Hey everyone, welcome to Abstract Algebra I. This is going to be the first lecture of the course, and in this section we're going to get some preliminaries out of the way. There'll be two lectures, two sections of preliminaries that we'll cover, and the first one we're going to talk about properties of integers and get some kind of commonly referenced properties under our belt. Some of these things you'll have seen. Probably most of them you will not have proven. We're going to go through some proofs. And then the second thing, we're going to briefly introduce modular arithmetic. It'll come up in a variety of places in abstract algebra, so we want to familiarize ourselves with it. So let's go ahead and get started. We'll call this section 1.1. Again, preliminaries, properties of integers, and modular arithmetic. Okay, so much of abstract algebra is going to involve properties of integers and of sets generally, and so the goal here again is not to obviously provide an exhaustive inventory of the properties of integers, but instead to kind of touch on some of the key things and kind of prep ourselves with some key notions that will be used throughout the rest of the course. Okay, and we're going to start with the well-ordering principle. The well-ordering principle we're going to take as an axiom. The property cannot be easily proven, it cannot be proven, period, from the usual properties of arithmetic. So we're just going to assume it. So we're going to take this as an axiom. Okay. This is an unbelievably simple principle, but it has a lot of power, and as you'll see, several of the proofs that we'll work through today in this section rely on it. So the property basically says every non-empty set of positive integers contains a smallest member. It's that simple. So every non-empty set of positive integers contains a smallest member. Okay, so pretty straightforward axiom, right? If I've got a set of integers, and there's at least one integer in there, then all this is saying is that there's the smallest member in the set. Right, pretty straightforward. And so this is going to come up in a couple of proofs. The first one that we're interested in is the division algorithm for integers. We need to have a good understanding of how the division algorithm works, and we want to be able to prove it, and the well-ordering principle is important for that proof. So let's start by kind of talking through some of the aspects that'll come up in the division algorithm. The division algorithm for integers. Okay. So we say that t not equal to 0 is a divisor. It's a divisor of an integer s. We say that t not equal to 0 is a divisor of an integer s if there exists a u in z, some other integer u, such that s is equal to t times u. Okay, so this is the idea of a divisor. So t, obviously we know t has to be non-zero. It's a divisor of s if there exists this other integer u such that s is equal to t times u. Okay, and so the notation here, if t divides s, we write this notation, we use this notation. So t divides s. Okay, that's the notation. If t does not divide s, we kind of do the same thing except a little slash. So t does not divide s. That's the notation we'll use. This is pretty common, pretty typical notation. Okay. And so a prime number then would be a positive integer where the only divisors are 1 and itself. Right? A prime number, it's a positive integer, we know that. And it's a positive integer whose only divisors are 1 and itself. Now, trivially, everything is divisible by 1, right? And also everything is divisible by itself. And so what this kind of means is that primes have no divisors, right? In the non-trivial sense. Okay, and kind of a closely related idea is the idea of a multiple. So an integer s is a multiple of t. It's a multiple of an integer t if there's an integer u such that, well, such that s is equal to t times u. Right? So saying that t divides s is the same as saying that s is a multiple of t. Okay. Okay, so multiple. This is another idea that is all kind of related to this division algorithm. Okay. So let's state the division algorithm. We'll state this as a theorem and then we'll prove it. So we're going to let a and b be integers. A and b are integers with b greater than 0. Then there exists a unique q and r, right? A unique q and r integers again with the property that a is equal to b, the divisor, times q plus r, the remainder. Okay, and so b here is playing the role of the divisor. R is what we call the remainder. All right, so these are terms you've obviously heard. We just talked about divisor, but remainder is another one. And so a and b are integers, b greater than 0. Then there exists a unique q and r with the property that a is equal to b times q plus r. Now, importantly, 0 is less than or equal to r, which is less than b. Right? Now, if r is equal to 0, then this is just a equals bq, and we say that b divides a in the case where r is equal to 0. Now, where r is greater than 0, we say that b does not divide a, right? There's some remainder. Okay? So this is stuff we've seen before. I'm sure you've seen this before. Okay. Let's do a couple of examples, and then we'll, just to get more comfortable with this, if we're not comfortable with it already, and then we'll prove it, and we'll write a quick proof of this one. So example, let's let, well, for a equals 17 and b, the divisor, equal 5. Right? We could write, so for our a equals bq plus r, we'd write 17 is equal to 5 times what? Well, it goes in there 3 times, doesn't it? And the remainder would be 5 times 3 is 15, so the remainder would be 2. Okay, so q is equal to 3 and r is equal to 2. Now notice that 0 is less than or equal to 2, which is less than 5. And there's no other possible q and r combinations, right? If I make q equal to 4, then I've got 17 is equal to 5 times 4, which is 20, and I'd have to make my remainder negative, which would violate the property that the remainder be between 0 and b. If I make my q equal to 2, then I've got 17 is equal to 5 times 2, which is 10, which would make my remainder 7, And so at that point, my remainder would be larger than b, which would again violate this range. Right, so this q and this r really are unique. Okay. Another example. Let's say a equals negative 23 and b is equal to 6. Okay, so then I could say negative 23 is equal to 6 times, well, I could go negative 4, right? 6 times negative 4, that's negative 24. And my remainder would be 1. Okay, now notice here that 0 is less than or equal to my remainder of 1, which is less than b, which is 6. Okay, so in this case, this product here is larger in absolute value than this, but that's because it's negative, so it has to go that direction in order to make the remainders fit. Right, so when you're dividing a negative number by a positive number, you have this kind of odd relationship, but again, it fits the pattern, it fits the theorem perfectly. Okay. All right, so hopefully you get the idea here, and that's not too difficult. So let's go ahead and write a proof of this theorem. Okay, so just stating it one more time, let a and b be integers with b greater than 0. Then there exists a unique q and r, integers again, with the property that a equals b times q plus r, and this r is between 0 and b. Okay, so that's the division algorithm, the statement. We'll state it again. And then let's go ahead and, oh, that's the theorem, sorry. And let's go ahead and prove it. Let's write the proof. So there's a number of ways to prove this. I'm just going to kind of go with the one that I recall seeing when I was taking this course for the first time. We're kind of going to prove it in 2 steps. We start first with the existence, right? So prove that no matter what a and b integers are given, there's going to be some q and r that makes this true. And then we'll secondarily prove the uniqueness of q and r. Okay, so we'll kind of do it in 2 steps. So we'll start with 1, right? And so to start with, we're going to create a set. We're going to let S equal the set of a minus bk such that the k is an integer, right? A and b are, from the theorem, they're integers. K is some integer, and a minus bk is greater than or equal to 0. Okay, so what is S here? Well, this set S is just the set of all possible remainders, right? Right, so we have a equals bq plus r. If I subtract the bq, I have a minus bq equals r. And that's what this is basically going to be. Here we're not putting any upper bound on the remainders. We're just simply saying that the remainders are all, we're looking at all the possible positive remainders. Okay. All right. Okay. So first thing we can say is if 0 is in S, right, the number 0, if 0 is a possible remainder here, then b is going to divide a. Right? If it's possible to find an integer such that there's no remainder, then that means b divides a. Okay, and so if b divides a, then q is equal to basically just a over b with a remainder of 0. Okay. Right, so we're going to assume that 0 is not in S. Okay, so if 0 is there, then b divides a, and we're done. So assume 0 is not a member of S. Okay, now we know that S is non-empty. That's easy to think through. Right, there's definitely some integers that we could divide another integer by and get a remainder that's positive. That's definitely possible for any number, right? So S is clearly not empty. And I'll write that S is not equal to the empty set. And so because S is not equal to the empty set, we can apply the well-ordering principle. We can apply the well-ordering principle. What did the well-ordering principle say? Well, it says that given a non-empty set, there's a smallest member. Okay, and so there's some smallest member of this set S. So we can apply the well-ordering principle and let R equal A minus BQ be the smallest member of S. Okay, so because the well-ordering principle works, it exists, we know that there's a smallest member of S, and we're just going to call it R and let it be equal to A minus BQ. Okay, so we're fixing this K as some Q now, right? Okay, so given this, A is equal to B times Q, that's a Q, plus R, and R we know is greater than or equal to 0. Right, so what do we need to show? Well, to show existence, we need to show that R is less than B. Okay, we need to show that R is less than B. Okay. Right, so A is equal to BQ plus R, and R is greater than or equal to 0. So we wish to show that R is less than B. If we've done that, then we've shown that for this arbitrary integer A and this arbitrary divisor B, then there exists this Q and R. We haven't shown uniqueness, but we'll have shown existence if we can show that R is less than B. Okay, so let's assume that R is greater than or equal to B. Okay, so let's assume that R is greater than or equal to B. Okay. Then A minus B times Q plus 1 is equal to, let's look at this guy, A minus B times Q plus 1, so increase Q by 1. This is going to be equal to A minus BQ minus B, right? This A minus BQ, we know that that's R, right? Right, this is just R, so that's equal to R minus B. Obviously, that's greater than or equal to 0. Okay. And so what does this show us? Well, this shows us that A minus B times Q plus 1 must be an element of S. Right? It's one of those remainders, isn't it? Right? But what's the problem? Well, but A minus B times Q plus 1, this has got to be less than A minus B times Q. Why is that? Well, A is a positive number in both cases. Here I'm multiplying it times, or I'm subtracting off B times Q plus 1, which is going to be larger than B times Q. So I'm starting with the same thing and subtracting off something larger here, right? So this is definitely going to be smaller than A minus BQ. Right, but this contradicts our assumption that A minus BQ is the smallest member of S. So this contradicts our assumption that R equal A minus BQ is the smallest member of S. Right? And this this problem, this contradiction stems from this. Right? And so we'll have to at this point understand that in fact R must be less than b. Sorry, this is r greater than or equal to b. Right? So r is less than b. And we're done with existence. Right? So we've proven that there exists a q and an r such that a equals bq plus r. Right? Where r, the remainder, is between 0 and b. Okay, so we've got the existence. All right. Well, what about uniqueness? So let's jump to uniqueness now. Let's talk about that part of it. Right? Right, so the way to prove uniqueness is to assume there exists some other q and r, right? So let's assume there exists q, q prime, r, r prime, such that a equals bq plus r, where 0 is less than or equal to r less than b, and a is also equal to b times q prime plus r prime, where 0 is less than or equal to r prime less than b. Okay, so assume this division algorithm works for two separate q's and r's. Okay, simple, right? And we're going to show that the q's and the r's have to be the same. Right? If this is true, this forces the q's and r's to be equal. So for convenience, and without loss of generality, let's assume that r prime is greater than or equal to r. It has to be one way or the other. Either r's greater than or equal to r prime, or r prime is greater than or equal to r. No matter either way you formulate it, you can set up the same argument. You just have to kind of change the order of things, but both directions work, obviously, right? So if this is true, then because these are both equal to a, we can equate them, and so I get bq plus r equals bq prime plus r prime, right? And I can move some things around here. Right, I can bring the bq prime over here, bring the r over there, and so I can get to bq minus bq prime equals r prime minus r pretty easily. And I can do a little bit of factoring here, and I get b times q minus q prime is equal to r prime minus r. Okay, and so here's kind of a subtle little trick, right? We can, by writing it in this way, what this shows is that b divides r prime minus r. Right? So r prime minus r is some positive integer, in this case positive integer, and I can divide it by b, right? Because this q minus q prime is going to be some integer. Okay, and so what do I have here? So let me grab another page here. So what I can say here is that b divides r prime minus r, right? B divides r prime minus r. And another thing that we can see from this is that 0 is less than or equal to r prime minus r, and r prime minus r is definitely less than or equal to r prime, which we know is less than b. Right? So we've bounded this r prime minus r between 0 and b. Okay. Okay. And so notice that r prime minus r is less than b, right? Obviously, you've got this here. And if b divides r prime minus r prime minus r must be 0, right? So r prime minus r is less than b, and b divides r prime minus r, right? So these two facts together imply that r prime minus r equals 0. And what does that mean? Well, that means that they're the same number, right? So r prime equals r. Okay, and then at this point, it's clear that q prime equals q. Okay. All right, so this is kind of a subtle point here, right? By bounding r prime minus r as being less than b, strictly less than b, and also saying that b must divide r prime minus r, which is what we caught up here, then the only way that can be true is if r prime minus r is 0. Okay, because 0 is less than any of its divisors, but it's also divisible by any of its divisors, right? Obviously, divisors. Okay, and so that's where we get uniqueness. So that implies uniqueness. And that's enough, right? So we've got existence and uniqueness. So we know that for any integer a and b, any integers a and b, there's going to be a unique q and r with the properties that a is equal to bq plus r and r is between 0 and b. Okay, if r equals 0, that means we've got a divisible, that a is divisible by b. Okay, very good. All right. Okay, so that was our first little proof, and it's somewhat tricky. I mean, if you're not kind of used to this sort of thing, it can feel a little tricky, right? So that's pretty normal. So in this setup, in this context, q, right? What is q? Well, q is called the quotient. So we had a equals b times q plus r. Here, b is the divisor, q is the quotient, and r is the remainder. Right? These are all terms you will have heard for sure. Okay, so you got the quotient, the divisor, and the remainder. Okay. All right. So the next thing what we want to move into next is another important property of integers, and something that's going to rely on the well-ordering principle for the proof. And this is going to be, well, this is just the definition, and we'll get into a theorem in a moment, but the definition of the greatest common divisor. So the greatest common divisor of two non-zero integers, a and b, okay, is the largest, and this is kind of self-explanatory, is the largest of all common divisors. Of a and b, right? Right, so obviously people will have heard of the greatest common divisor. The greatest common divisor of two non-zero integers a and b is the largest of all the common divisors of a and b. Okay. So just to make sure, just a level set here, the greatest common divisor of 4 and 15 is 1. Right? You can think about all the divisors of 4. 4 is equal to 2 times 2. It's also equal to 4 times 1. You can think of all the common divisors, the ways to break up 15. That's, you got basically 3 times 5 and 15 times 1. Right? And the only thing common to both lists is the 1. Right? So that's the greatest common divisor there. Okay, another example. The GCD of 4 and 10 is equal to 2. So again, 4 is 2 times 2, 4 times 1. 10 is 2 times 5, 10 times 1. Right, and so you can see 2 is on the list there. 2 is the largest divisor of both integers. All right. Okay. And so it's not always obvious how to find the greatest common divisor. Sometimes the GCD is quite large. this next theorem, so the next theorem is going to play a really critical role in abstract algebra. We'll see it in a lot of different places. It's basically tells you, gives you a way to find the smallest positive integer. It's not the most practical way to find the smallest or the smallest positive integer, or the greatest common divisor, but it's one that has a lot of not practical value, but theoretical value. Okay, so the theorem goes like this: for any integers a and b, right? So for any integers a and b, where both a and b are non-zero, so any two non-zero integers a and b, right? There exists an s and a t integers such that the greatest common divisor of a and b is equal to as plus bt. Okay. Right, so there's more to the theorem, but let's pause for a second. So given two integers a and b, the greatest common divisor of a and b is going to have this form, as plus bt. Now this is like a linear combination of the integers a and b themselves, right? So that's kind of interesting, right? So this is telling us that the GCD has a certain form, and the form is a times some integer plus b times some integer. So it's a linear combination of the two integers in question. Okay. Now, moreover, the GCD of a and b is the smallest positive integer of this form. Okay. Right, so if you were able to just enumerate all of the integers of this form, the smallest one is going to be the greatest common divisor of a and b. Okay, so that's a very interesting theorem. I don't know that I wouldn't have anticipated this going into the GCD question, right? When someone first defined the GCD, I wouldn't have said, oh, the GCD is going to be of the form as plus bt. It's going to be a linear combination of a and b, and the smallest such combination of this form is the GCD. I wouldn't have thought that'd be the case. Okay, but it is. It is. So let's take a look at the proof of this theorem. Okay, and so again, we're going to make use of the well-ordering principle. So we're going to start with a set. So we're going to let S equal the set AM plus BN, where M and N are integers. Okay, and AM plus BN is greater than 0. Okay. Right, and so this kind of mirrors the requirements of the theorem, right? So AM plus BN, that's your AS plus BT, and obviously M and N are integers, S and T are integers, and the smallest positive integer of this form is the GCD, so this is why we bring this in. Let's just consider the positive linear combinations here. Okay, and so that's what's happening with this set S. Okay, and so S is obviously not empty. Takes about 10th of a second to think of an example of something in S given any two integers a and b. So S is obviously not empty, right? So S is not equal to the empty set. So the well-ordering principle asserts that S has a smallest member. So S has a smallest member by the well-ordering principle. Okay, perfect. Okay, we're going to let this smallest member, we're gonna name it. Right, so let the smallest member of S be, and we're going to call it D. and d is equal to as plus bt. Right, so we're kind of fixing m and n and calling them s and t now, right? So s and t are some fixed integers such that we are looking at d, the smallest member of s. So what do we need to show? So we wish to show what? That d is equal to the greatest common divisor of a and b. Okay. All right, it's clear so far, hopefully. Okay. So we wish to show that this d, which is equal to as plus bt, it must be the greatest common divisor of a and b. Okay. So let's consider the division algorithm. So we'll consider the division algorithm, right? And so a is equal to d times q plus r. Right, and this is basically saying that d is a divisor of a, right? We're assuming that d is a divisor of a, right? If it's the GCD, then this must be true, right? So we're going to start with this. We're going to assume that a is equal to dq plus r, and in order for this to be true, 0 needs to be less than or equal to r, which needs to be less than d. Okay. All right, so assuming that r is greater than 0, well, if r is greater than 0, then what? Well, we could say that r is equal to a minus dq, which would be equal to a minus, now what is d? D is as plus bt, right, times q. And just doing a little bit of algebra to this expression here, we'd get a minus asq minus btq. Okay, we could do a little factoring here. This is pretty straightforward. A is going to be equal to 1 minus sq minus b times, well, plus b times negative tq. Okay, and this is just your m, and this is just your n. So this is am plus bn, right? We've got that form. And so that means that r is in S. Okay, this is again going to be a contradiction, right? So the remainder greater than 0. So we assume the remainder is greater than 0, and that implies this whole thing here, which means that r is in S, and this contradicts the idea that d is the smallest member. This implies a contradiction that d is the smallest member. Okay. All right. And so what does that mean? Well, it means that, r must be equal to 0. That's going to imply that r is equal to 0 then, right? So we got to overturn this and imply that r is equal to 0. And if r equals 0, then what we're saying really here is that, this is 0. That means d divides a. Okay. Very good. So d divides a. All right. Now the same thing can be done for b, right? We started with a, right? We considered the division algorithm, a equals dq plus r. The exact same argument could be applied to b. Nope, could be applied to b. Right, so hopefully you can see that it doesn't really matter. If it's true for a, it's obviously true for b as well. We could do the same argument for b. Okay. All right. Okay, so what do we have so far here? Well, what do we know? Well, D divides A, and D also divides B, right? And so what that means then, obviously, is that D is a common divisor of A and B. Right? It's a common divisor of A and B, that much is clear. Right? It's a common divisor of A and B, but is it the least common divisor? So next we wish to show that D is the least common divisor. So how would we go about that? Well, let's just choose some other value as a common divisor, and we'll show that by necessity this other value must be larger than D. Right? So let's let D prime be another divisor, common divisor of A and B. Okay, so we've got this new number, D prime, which presumably is not the same as D, and it's a common divisor of A and B, right? So what do we know then? Well, we know if it's a common divisor of A, we know that A is equal to D prime times some integer h, and if it's a common divisor of B, we know that B is equal to D prime times some integer k. Okay. Now D itself has the form AS plus BT, right? Okay, and so this is going to be equal to D prime H times S plus D prime K times T, right? And so we can clearly rearrange some things here and factor out the D prime, and we get HS plus KT. Right, and so this is just, so what does this say? Right, so this is saying that D is equal to D prime times some integer HS plus KT. And what does this mean? Well, this just means that D prime divides D. Okay, so if D prime divides D, then D prime must be smaller than D. And so, I mean, that's just all that says is then that D is a larger number. So D is they're both common divisors, but D is greater. So D is the greatest common divisor of A and B. Okay, so that's how you get it. Right, the way we've described D as being the smallest member of this set kind of implies that it's automatically the GCD. Okay, very good. All right, so so this is a powerful result, and we'll use it lots of times throughout the course. But in reality, in practice, it's not a great method for actually identifying the GCD. So this result is powerful, but it's not practical. It's not a practical method for identifying the GCD. Right, so we'll use it. It'll come up a lot. We'll use it to prove things. We'll use it to make assumptions about the form of the GCD, etc. But we won't. In practice, you wouldn't want to use it to find the GCD. Right? To find the GCD, we'll actually use the Euclidean algorithm. And this is an algorithm that's literally from Euclid's Elements, Book 7, right? It's from Euclid's Elements, Book 7, I believe. Okay. So this is from book 7, and this is going to be, I'll kind of state it here, and we'll go through why it works. I don't know if our derivation will rise to the level of a proof exactly, but you should be able to see why it works by the end of this. So here's the setup, and we'll restate. Well, no, this is we'll just kind of describe it here, and we'll do an example or two. But so here's basically how it works. So for any pair of positive integers, so for any pair of positive integers a and b, we'll say, okay, we can basically find the GCD by repeated use of the division algorithm. Okay, by repeated use of the division algorithm. And what's going to end up happening is, as we repeatedly apply the division algorithm, we're going to do it in such a way that we step the remainder down. Right? The remainder is going to get smaller and smaller until eventually the remainder will be 0. Right? And as part of this process, we'll be stepping down the divisor. And when we get to the end, this final divisor is actually going to be, the final divisor will actually be the GCD. It kind of depends on how you set it up, but I'll show you what I mean in a second here. Okay, so we will produce a decreasing sequence of remainders. Right, and so it'll be, we'll start with the first remainder, and then we'll have a smaller second remainder, and so on until we get to 0. Okay, and then when we get to this, the one right before 0, that's going to be our GCD. Okay, so here's what it kind of looks like. So we start with a and b. Given a and b, we say a is equal to b times, we'll call it q1 plus r1. Right, so this is just the first application of the division algorithm. And so we know here that 0 is less than r1, which is less than b. Okay, now the assumption here is that r1 is not 0, right? Because we have to, if r1 were 0, we'd be done, but we have to keep going, right? We have to keep going until r is equal to 0. Right, so normally this is less than or equal, 0 less than or equal to r1, but in this case it's less than strictly. Right, and so then what we do is we use the divisor, right? The next iteration, the divisor b becomes the thing you're dividing, and we divide it by the previous remainder. Right, so we get something like this. And so again, here 0 is less than r2, which in this case would be less than r1. Right, and so then after this first iteration, everything just kind of proceeds, right? So then r1 is equal to r2 times a new quotient, q3, plus r3, right? And in this case, 0 is less than r3, which is less than r2. So you can see that the way we're nesting these remainders, this is necessarily a decreasing sequence, right? Right. And if we were to go on, the next one would be what? The next one would be r2 equals r3 times q4 plus r4, where 0 is less than r4, which is less than r3, right? And so on. We continue on like this until we get down here, and let's say rk minus 2 is equal to rk minus 1 times qk plus rk, right? And here 0 is less than rk, which is less than rk minus 1. All right, and then the final iteration would look like this. Rk minus 1 is equal to rk times qk plus 1. And in this case, at some point, the remainder will be 0 by necessity. It has to diminish to 0. Okay. Right. So the well-ordering principle is going to guarantee that the process must eventually result in a remainder of 0. Okay. And so then rk, you can think of it as either the last non-zero remainder or the last divisor, however you want to think of it. It's the last non-zero remainder or the last divisor. I think it's probably easier to think of it as the last non-zero remainder, right? So rk, the last non-zero remainder, is the GCD of A and B. Okay. All right, so we'll get to why the heck this works in a second. Let's do an example just so we can make sure that this process makes sense, because it seems a little cumbersome at first. But you'll see that when you're using real numbers, it's relatively straightforward. So let's do an example that isn't trivial. Let's find the GCD of 2,520 and 154. This is not one you can just kind of guess at. It's not one you can just list all the factors on either. All right, so let's start with the first line. The first line we would say A equals BQ1 plus R1. So what is that? Well, we would start with 2520 equals 154 times, what's the quotient, the first quotient? Well, 154 goes into 2520 16 times, it turns out, and the remainder is 56. Okay. Then our next level would be B equals, and we want to divide it by this remainder, R1 times some Q2 plus R2, right? And so in this case, it's going to be 154 is equal to, we got to divide by the previous remainder, 56. And 56 goes into 154 2 times, and the remainder is 42. Okay, so you can see the remainders are dropping off, as they should. So then the next iteration would be R1, this guy, is going to be equal to R2 times some Q3 plus R3. All right, so here we would have 56, the previous divisor, is equal to, we divide that by the previous remainder, which is 42. 42 goes into 56 one time, and the remainder is 14. Okay, and then we would have R2 equals R3 Q4 plus R4. Okay, and so that's 42 equals, divide that down by 14, goes in there 3 times, and the remainder is actually 0. So you just do this process until the remainder is 0, and the last non-zero remainder is the GCD, so that means this is the GCD. So the GCD is 14. Okay, and so that's exactly what you would want to see. All right. So that's fascinating, but why in the world does this work? Okay, why does this work? What is going on here, really? Okay, why does this work? Well, let's take a look at this. So to see that R of k is equal to the GCD of A and B, let's consider the last few iterations of the algorithm. So let's consider the last few iterations of the algorithm. Okay, what's going to happen here? So what we would end up with is r of k minus 3, we'll say, is equal to r of k minus 2 times q of k minus 1 plus r of k minus 1. Okay, right, and I'm just going to label this. We're going to need to refer to these, so I'm going to label them. And then we would have r of k minus 2 is equal to r of k minus 1 times q of k plus r of k. Right, now this is actually going to be our GCD, but then what happens in the next iteration? R of k minus 1 equals r of k, q of k plus 1 plus 0, right? So this is the last few iterations of this algorithm. Okay, and so what we're going to do is we're kind of step back through this. So from 1, we can see that r of k divides r of k minus 1. Right? Okay, so that's straightforward here. So r of k divides r of k minus 1 because the remainder is 0 here. Okay, and then from 2, we have, what do we have? Well, r of k minus 2 is equal to r of k, just kind of reading it off here, r of k minus 1 times q of k plus r of k, right? And now we have an expression for r of k minus 1, which is this. Okay, so that's equal to r of k times q of k plus 1 times q of k and then plus r of k. Okay, so again, I'm just substituting r of k minus 1 into this expression right here. And that's what you get here. And then we can factor this, right? We know there's a factoring here that can take place, so we can factor an r of k out of both. And you get q of k plus 1 times q of k plus 1. And so you get this. And so obviously that, so r of k minus 2 is equal to r of k times this thing, right? So that means r of k divides r of k minus 2. Okay, so we've got that r of k divides r of k minus 1, and now we see that r of k also divides r of k minus 2, and so this can continue on up the chain. Right. So similarly, r of k divides r of k minus 3, right, and so on. And you can keep this up until you see that r of k divides b, and ultimately r of k divides a, right? And so this is how you can see that r of k is a divisor of a and b. Right, so you can get to the fact that r of k is a common divisor of a and b using just this kind of, just basically reversing the process and substituting at each step. Okay, so it's clearly a divisor, but how do we know it's the GCD? How do we know it's the greatest common divisor? How do we know it's the greatest? Well, the way to do that, the way to see that is to assume that r is a different common divisor. So let's assume that r is a different common divisor of a and b. Okay. Okay, so then from the previous thing, we saw that a is equal to b q1 plus r1, right? And r dividing a implies that a equals r times bq plus r1, right? Okay, and in that second equation, we had something similar. We saw that b is equal to r1 Q2 plus R2. Okay. And R dividing R2 implies that B is equal to R times R1 Q2 plus R2. Okay, so we can see that. Again, we're just kind of substituting this R through from the top down. And then going on like this, we'll see that R ultimately divides RK. All right, we'll see ultimately that R divides RK. Now, if R divides RK, right, RK is obviously not 0, then RK must be larger than R. So the implication here is that RK is greater than R. Right, and if that's the case, then RK is the greatest common divisor, right? This R is totally arbitrary, so RK must be the greatest common divisor. And that's what we wanted to show. So that's the result we're after. Okay. All right. Very good. So that's the GCD, and so we've seen the form of the greatest common divisor will take, and we've also seen how in practice we would actually want to use the Euclidean algorithm to identify the greatest common divisor. Right, and so we kind of saw why that works as well. Okay, so I think I'll break this lecture into 2 sections given the length. So this will be the end of part A, and then we'll record a part B to accompany this one. So we'll see you in part B.